All right, so we're going to start out with some atom structure, history, okay, that kind of thing here, because, well, the atom is the basic unit of matter and thus the basic unit of chemistry, of course. If you've seen any of the Oppenheimer stuff that came out this summer, okay, you'll know that physics was in fact the science that discovered the atom, and that chemistry can thank us for that, because without physics there would be no chemistry, and without chemistry there would be no biology, because biology is just applied chemistry. The biology teachers and chemistry teachers have a different story, but they're wrong. Just saying. All right, so the key points for today, and guys, anytime you get a lesson in my class, there'll be an initial slide that has the key points. That's the stuff to watch for. Okay, that's the stuff that ends up on, say, Thursday's quiz, okay, something like that. So understand how the theories of the structure of the atom were developed. So basically, why did people think the atom was a solid sphere, and then they thought it was plum pudding, and then they thought it was this thing. Okay, kind of why our understanding has changed over time. Okay, and then learn the parts of the atom and their characteristics. That's probably going to be a review because you probably already know what makes up an atom. Okay, but we go over it again, okay, in terms of the structure and the currently accepted model of the atom. Okay, so alchemy and the birth of chemistry. So before the idea of the atom was even really a thing, okay, there were people that were doing, let's say, work to do with the physical and chemical properties of matter. Okay? Now, it wasn't true chemistry because there was no scientific method at the time. It was a secretive kind of pursuit, okay? And we called it alchemy. It was basically just trial and error kind of stuff. I mixed these two things together. How can I turn lead into gold? How can I make the elixir of life that makes you live forever? Okay, those kinds of kind of harebrained pursuits that we know now are not going to happen. Okay, at the time, of course, because they didn't understand the structure of matter and the behavior of matter, they did believe that these were things they could do. Okay, because they saw when a chemical reaction happened, they started with this stuff, and when they were done, they had this stuff. And they didn't understand what had happened in that reaction from an atomic level, so they figured there must be a way to turn lead into gold. Okay, I turn this stuff into that, why can't I turn lead into gold? Well, it works a little differently. Okay, we'll kind of go into that a bit here. Okay, but we've been using chemistry for a long time, applying it for practical purposes without really always understanding how or why it worked. Okay, so things like dyeing cloth, tanning leather, preparing foods, okay, things like that. All right, so the earliest atomist, we'll say, okay, the first person to propose that maybe matter was made of these tiny little particles was actually a Greek philosopher, and his name was Democritus. Okay, and he proposed that matter was made of indivisible, okay, indivisible, not invisible. Okay, there's two different things. Right, indivisible means you can't split them. You can't cut them. Okay? They're the smallest that matter can be. Okay? And he called them atoms, or atomos, which means uncuttable. Okay? So the atom comes from the Greek word atomos, which means not cuttable. Right? His ideas were overshadowed, however, because people like Aristotle, okay, and other Greek thinkers believed that matter was made of 4 elements. Okay? And those 4 elements would be what?
Water, earth,
air, and
fire.
Okay, now that made way more sense to the common person. Okay, because they had almost like a periodic table of sorts. Okay, for example, steam. Steam was some parts water, some parts fire, and some parts air. Okay, it made total sense. You mixed fire and water, and you got steam, which kind of took off and went off into the air. Okay, so it made sense to people at the time. What's that?
It's water in the air.
It's water in the air, right? The Greeks were very familiar with lava, okay? Volcanic eruptions, okay? Lava was some parts earth and some parts fire and some parts water, okay? Because it could flow, all right? So, they had this system that made a lot of sense, and it was, something they experienced and just made better sense than, hey, everything's made of these tiny particles you can't see. Oh, that's convenient. I can't see them. What's your proof? Okay, so people didn't really go for his idea, even though thousands of years later, he ended up being proved right. Okay, so when he first proposed this idea, okay, yeah, people didn't really accept it. Okay, so being a Greek thinker, that was like the best job you could have in ancient Greece. Okay, you sat in the Parthenon and people fed you grapes and fanned you with a big palm leaf, and you just had to sit there and come up with ideas. Okay, so it was a pretty sweet job. Okay, but the day Democritus came up with the idea of the atom, people probably like, are you fanning him enough of that thing, or has he been sitting in the sun too long? Because that idea seems a little crazy. Okay, but we do now, of course, know that it is in fact true. Now, it wasn't all bad for Democritus. He did come up with something else. Sounds like his name.
Democracy.
Democracy. So he was more of an arts guy than a science guy in the end. Okay, came up with some good stuff. Okay. All right, so the alchemists. Okay, so the alchemists would have had, kind of like this, Da Vincian kind of laboratory. What's that?
Rube Gold machine.
Yeah, like exactly, like Rube Goldberg. Like they would have had all these weird vessels and stuff inside of their, kind of little closed-in caverns that they would work in. Okay, and they would be coming up with, different things. They would just mix stuff together and see what happened. Okay, like probably gunpowder was probably invented like 10, 12 times before somebody lived through the explosion to tell the tale. Okay, but that's basically all they did. There wasn't a lot of, I have a hypothesis, here's a procedure to test it, I'm going to come up with a conclusion. It's like, what am I mixing today? Okay, and how, who's going to drink my potion today? Which is basically like, who's going to die today? Okay, but yeah, like it was that kind of stuff. That's what they were doing. It wasn't chemistry because it wasn't using the scientific method, but they were investigating the behavior of matter. Okay? And some important stuff was discovered during that time, but again, there wasn't a lot of communication either. Good science does require that you communicate and share your ideas so that other people can replicate your research and then prove its validity. Okay? There wasn't a lot of that going on in alchemy, because if somebody figured out how to turn lead into gold, they weren't letting that secret out. Okay? They were going to keep that one to themselves. All right, so after alchemy, okay, after kind of the Dark Ages, okay, Roger Bacon and Antoine Lavoisier came up with the scientific method, okay, which kind of started with chemistry. And in the scientific method, okay, they devised this idea that if you're going to do good science, good research, it's not just mixing two things together today. Okay? It's, here's a problem you want to solve. Here's what you propose the solution is, your hypothesis. Here's the materials you're going to need to test that hypothesis. Here's the procedure that you and others are going to follow to test that hypothesis for validity. Okay? Here's the data you're going to collect. Here's the analysis you're going to perform on that data. And then you're going to use that analysis to come to a conclusion as to whether your hypothesis is valid or not. Okay? So like a lab report works. Okay? That's the scientific method. Right? They're the ones who devised that. And once that was applied, science took off. All sciences took off, because now things were being done in a more scientific manner. Okay? And we were communicating data, we were sharing data, okay? Things like that. So they're important in that they came up with the scientific method. Nothing really for chemistry other than they came up with the scientific method. Okay? Guys, if you have questions as we go, don't be afraid to ask. Okay, so the idea of the atomic theory. Obviously, we already said that it was Democritus that came up with that idea initially. But we had to kind of explain some of the behaviors of matter. People realized that when they started observing reactions and things like that, that matter didn't behave like it was made of 4 elements. It behaved like it was made of tiny pieces. Okay? And those tiny pieces were moving around, and they could join with each other, and they could separate. And so the 4-element idea really didn't explain the behavior of matter very well once we kind of got into the science of it. Okay? So people started coming up with other ideas. Okay? Now, the idea of the atom is that it is the smallest form of an element that can exist, okay, and still retain the properties of that particular element. All right? So if I have an atom of lead and I have an atom of oxygen, they are going to look different. If I could see them, they would look different. Okay? They would have different properties. They would have different numbers of protons, neutrons, and electrons, okay, because they are different elements, but they still retain the properties of lead, okay, a soft silvery metal, oxygen, a colorless, odorless gas. Okay? They would still have those properties. but I couldn't make them any smaller. Okay? If I was to cut one of those atoms, it would no longer be an atom of lead, okay, or an atom of oxygen. It would be something else. Okay? That's what happens in nuclear fission. Okay? In nuclear fission, you physically actually break atoms apart and they become other things. Okay? That sort of making sense? Okay. All right, so the atom, as we said here, is the smallest, okay? And it is the smallest particle of an element that retains the properties of that element. Right? Now, do you ever have to worry about accidentally splitting an atom?
No.
Yeah. Okay? Like if you're cutting carrots for soup, you don't have to worry about splitting an atom with a knife. Okay? The sharp edge of the knife is literally thousands of atoms thick. Okay? It would be like basically trying to, let's say, cut an apple with a sledgehammer. Okay? You could pulverize it, but you couldn't cut it. Okay? So that's not going to work. All right? You don't have to worry about splitting the atom by doing anything like that. Okay? Atoms are split by incredibly technical processes. Okay? So they're very, very, very small. What's that?
You use the atoms to split the atoms.
Exactly. You use atoms or other small particles, okay, free neutrons and things like that, to break atoms apart in nuclear fission, or you use incredible heat and pressure, okay, to fuse atoms together, okay, to make a different atom. Those are the only two ways you can change an atom, okay, is by nuclear fission or nuclear fusion, okay, and those things don't happen in everyday life, okay, it's not something you're going to make happen in the kitchen, okay, or something like that. All right. So if we're looking at an atom, okay, then our idea is that there is a nucleus, okay, and in that nucleus are the protons and the neutrons, the big heavy parts of the atom, okay, and then surrounding the atom, not in a ring like this, okay, but in a cloud, are the electrons. Okay, and the electron's position varies depending on the energy and energies of the various electrons, okay, which we'll talk about in a bit. All right. Okay. Now, John Dalton was the first person to take the data that was being collected about the behavior of matter, which I alluded to earlier, okay, that the four-element idea didn't explain what happened in chemical reactions very well, and so they needed a new idea of what the atom, or how matter was constructed. Okay? And what he realized was that Democritus' idea of small little particles actually made a lot of sense. Okay? It could explain how he could have two things react with each other and get two very different things at the end, okay? But why he couldn't turn lead into gold, okay? Lead and gold are elements. I can't change one element into another element. But if I react two compounds that are made of many elements together, I can get different things because I can rearrange their parts, okay, and come up with different combinations. Okay? That was very well explained by the idea of tiny particles, not so much by earth, air, fire, and water. And so Dalton came up with his atomic theory after quite a bit of experimentation. His first point he stole. That was Democritus' idea. Okay? All elements are composed of tiny, indivisible particles called atoms. Okay? Are these 4 points something you should know?
Yeah.
Definitely. That would totally be something I would put on Thursday's quiz. Okay? Dalton's atomic theory is crucially important for our understanding of the behavior of matter. Okay, all elements are composed of tiny indivisible particles called atoms. Okay? Atoms of the same element are identical. Atoms of different elements are different, okay, from those of other elements. Now, here's what we mean by that. Every oxygen atom will have 8 protons and 8 electrons. Okay? The number of protons is in fact what determines the physical and chemical properties of a particular element. Okay, so his second point basically says that atoms, while the smallest particle, are different for every element, and that's why different elements have different properties. Okay, now, this first part is not entirely true. Okay? Certainly all oxygen atoms have 8 protons. But
The electrons can vary.
the electrons can vary after a reaction becomes an ion. Okay? That's not as big a deal as the number of neutrons. Okay? There are things called isotopes. How many people have heard that word before? Okay, so an isotope is a form of an element that has a different number of neutrons. Okay? The bulk of oxygen atoms have 8 protons and 8 neutrons. Okay? Like, we're talking 99% of them do. Okay? But there's a very small percentage that would have a different number of neutrons. Those are going to be less stable and typically decay. Okay? How many people have heard of carbon dating? Okay, so carbon dating is how we tell how old something is, and it's because carbon has the same setup. Okay? Most carbon atoms have 6 protons and 6 neutrons. Okay? But some atoms of carbon have 2 extra neutrons, and that makes them carbon-14. Carbon-14 is very slightly radioactive and decays down into regular carbon. So we can tell by taking an artifact that we discover and looking at it and testing for how much carbon-14 is in it, how old it is. Because carbon-14 decays at a very predictable rate. Okay? So isotopes are not identical, okay, to other atoms of the same element. Okay? They're a little bit different. So this is essentially true, but not entirely, okay, because of the existence of isotopes. Okay, point number 3, atoms of different elements can combine with one another in simple whole number ratios to form compounds. Okay, now this part is important. Whole number ratios. That means you never have a fraction of an atom, okay, in a compound. For example, what's that stuff?
Water.
Water. 2 hydrogen atoms, 1 oxygen atom. Okay? Would I ever write water like this? No. I can't have half an oxygen atom. Half an oxygen atom is a beryllium atom. Or something. Okay? I can't have a fraction of an atom. We already said atoms are the smallest component of that element. I can't have half of something. So whenever you have a compound, you will never have a fraction in it. Okay? You could have H2O, or you could have CaCl2, okay? Or you could have C3H8. Okay? You could have all these different compounds, but they're all going to be whole number ratios. Okay? In the case of the last one, 3 to 8. Okay? 1 to 2, 2 to 1. Right? There's always going to be whole numbers of the individual particles. Everybody all right with that? Okay. His 4th point was the death of alchemy. Okay? The idea that I could turn lead into gold. Lead is an atom. I can't change the atom. Okay? In order to turn it into gold, which is another element, I would have to change how many protons and neutrons are in it. I can't do that. Okay? So, chemical reactions occur when atoms are separated, joined, or rearranged. Okay? This goes along with it. All matter is made of tiny particles. This is why we have that. It explains what happens in a chemical change. Okay? They cannot, however, be turned into different elements. Okay? So that was the thing that alchemy was trying to do, was turn one element into another. Okay? We can have a chemical change occur. We can have these 2 things turn into 2 different things. We can have 2 things combined to form one thing, but we can't change the elements involved. Okay? So, as an example, I could have, let's say, this reaction here. Okay? In that reaction, I have joined 2 atoms. I've joined magnesium and oxygen together. Okay? Did I create any new elements?
No.
No, I only have magnesium and oxygen on both sides. Okay? Is this going to look a lot different than these 2 things? Yes, it is. Okay? It's very different. All right? Because it's a different material. but it's still made of the materials, the elements that I started with, right? If I have this reaction is what makes your barbecue get hot. Okay, that's the combustion of propane. Okay, did I make any new elements? I started with carbon, hydrogen, and oxygen. And on the other side, I have carbon, hydrogen, and oxygen. Did I rearrange the elements? Yes, I rearranged them. Okay, carbon and hydrogen were together over here. Hydrogen's with oxygen over here. Okay, oxygen was by itself here, and it's in both things on the other side. Okay, I've rearranged, I've separated, I've rearranged the atoms. But they're still the same elements I started with. Okay? I'm never going to have a reaction that looks like this. Okay? I can't have that. I started out with lead, oxygen, and chlorine. I don't get gold from that. Okay? I didn't start with gold, I don't get to end with gold. Right? That just doesn't happen. Okay? So that's alchemy, and that doesn't work. And that's not going to work. Right? But other reactions where atoms are separated, joined, or rearranged, that's totally okay. And it can sometimes look like you've turned one thing into something else. That's why the alchemists thought they could do that, and that they could turn lead into gold. They saw themselves doing things where they turned one or two things into something else. Okay? So it seemed reasonable. Okay? They just didn't understand how matter worked. All right, questions on that? So make sure you know the 4 points. Okay? You don't necessarily have to memorize them, but know them well enough that you could write them out at least in your own words. Okay? All right, so Dalton comes up with this atomic theory, and everyone's like, wow, that's great. It really explains a lot of what we've been doing. So what do atoms look like? Dalton's like, I don't know. Can't you just be happy with what I did? It was really good. You said so. Why do I have to know what they look like? Didn't you read the first point? They're tiny and indivisible. I don't know what they look like. Well, that's not an acceptable answer for a scientist. So Dalton's like, okay, what shapes could they be? The sun is round. The earth is round. By the way, the earth is round. Yes. If you believe the earth is flat, this is probably not the right class for you. Okay? So the earth is round. The moon is round. Let's see, lots of things are round. Atoms are spheres. People are like, how do you know? I don't. But it seems reasonable. And everyone's like, okay. So he kind of dodged a bullet there. Okay? Sphere is a fairly common, naturally occurring shape. So let's go with that. Okay? Now, we know, of course, that's not what they look like, but it, at the time, at least explained the data that they had. Okay? They didn't know about how electrons can change, they can be transferred from one element or ion to another. They didn't know about any of that yet. So the solid sphere idea was perfectly fine. Okay? Now, it didn't last long. Okay? And it didn't last long because as soon as they started studying electrochemistry, okay, which is basically what we use to make batteries and things like that, the solid sphere model couldn't explain moving charges. Okay, or the change of charge from one particle to another, because there was no part of this that could come off. Okay, or that could be positively or negatively charged. It's just a ball. Okay, so it didn't explain what would happen in reactions where electricity could be produced as a byproduct. Okay. So, after Dalton comes up with the solid sphere model, J.J. Thomson, who's doing all these experiments in electrochemistry, says, we've got a problem. I'm doing these experiments and I produce electric current from chemical reaction. And the solid sphere model doesn't explain where that electric current comes from. We know we can't just create energy. Okay? The law of conservation of energy says you can't create it, you can't destroy it, so it's got to be there. It's got to be part of the atom. And the solid sphere doesn't explain where it comes from. So I'm going to change the solid sphere just a little bit. Okay? He didn't want to ruffle too many feathers because everybody kind of liked Dalton and what he did. Okay? So he said, we're going to keep the solid sphere, but we're going to say that embedded very loosely on the surface of the sphere are these negatively charged particles. Since they make electricity, we're going to call them electrons. Okay? And we're going to say that the solid sphere is positively charged, and these little particles, electrons, are negatively charged. And in a reaction, they get knocked off. And when they get knocked off, they can go over toward another atom, which is, they would be attracted to it because it's positive and they would go there. Okay? And that's how, electrons or charges can be created, or electricity can come from a chemical reaction. And people are like, we like what you did there. Okay? You showed some respect to Dalton by not radically changing his model. You explained your data, which wasn't explained by his model. Hey, good job. Right? And everyone accepted plum pudding for a while. Okay? But of course, it never stops there. Okay? Then people discover protons and they discover neutrons and they're trying to figure out the mass of particles and things like that. And then it just goes nuts for a while. Okay? And everybody starts coming up with all these different models of the atom trying to explain various things. Okay? None of which, by the way, involve a nucleus. Okay? That comes later. Okay? The idea of the nucleus was proven by a guy named Rutherford much later on. But we'll leave that for tomorrow. Okay? Because I can't finish it and I don't want to leave it in the middle. Okay? So we got about 5 minutes left here. Okay? But I'm going to leave it there for the next one.
Any questions?
Yeah, absolutely. A whole bunch of over there.